Welcome to the Explainer. If you're looking to completely demystify Docker and containerization, you're definitely in the right place. Today, our mission is to break down exactly how modern software development got absolutely transformed by, honestly, a surprisingly simple concept. So how did a simple metal box reshape the entire digital world? It's kind of a provocative question, right? But before we can talk about code, we really need to talk about cargo. How did a basic standardized metal box fundamentally reshape global trade and in turn provide the exact blueprint for reshaping our digital world? Okay, let's dive into this. Here's our roadmap. We're going to start with the shipping container analogy, then compare virtual machines to containers, break down the core Docker trinity, dive under the hood into Linux, explore multi-container apps, and finally look at massive scale orchestration. All right, Section 1, the shipping container analogy. Standardizing the world. To really grasp Docker, we have to establish its historical foundation. As Mark Levinson points out in his book, The Box, the physical shipping container literally revolutionized the global economy. Think about it. Before the container, cargo came in all these wild, non-standard shapes and sizes, and it was loaded haphazardly onto ships. It was incredibly slow and super expensive. The shipping container didn't revolutionize trade by being magic. It did it through pure, relentless standardization. Because every single box was exactly the same size, it could seamlessly move from a ship to a crane to a train to a truck. And that brings us to the absolute core takeaway here. Standardization creates portability. Just as standard metal boxes made global shipping incredibly efficient, Docker standardizes software. It packages your application and literally everything it needs to run into one uniform unit. What does this mean for us? It means it will run consistently anywhere, fixing that dreaded "it works on my machine" excuse that's been plaguing developers for decades. Moving right along to Section 2, virtual machines versus containers, the weight of emulation. To really appreciate Docker's value, we have to look at why the tech industry was desperately crying out for an alternative to traditional infrastructure. Before containers took over, we relied heavily on virtual machines. A virtual machine, or VM, is essentially a simulated mini-computer. It runs its own heavy, entirely independent operating system right on top of a physical server's hardware using a hypervisor. Now, while this offers fantastic security and total isolation, it is incredibly resource-heavy. Every single VM needs its own OS to run. That eats up memory, it hogs CPU, and you're looking at some seriously slow boot times. Contrast that directly with Docker containers. This is a game changer. While VMs virtualize the physical hardware, containers virtualize the operating system itself. A container actually shares the host's operating system kernel, bringing along only the specific files, environment variables, and libraries it actually needs. This makes containers extremely lightweight, highly efficient, and, get this, allows them to boot up almost instantly compared to the sluggish start of a traditional VM. Okay, Section 3, Docker files, images, and containers, the core trinity. These are the three essential interconnected components that make Docker actually function. First up, the Docker file. Let's think back to our analogy for a second. If we're building a physical shipping container, the Docker file is the initial requirements document or the engineering blueprint. It's a really simple text file that lists, step by step, everything your software environment needs, from the base operating system all the way up to your specific code dependencies. So, when you run a build command on that Docker file, it creates what's called a Docker image. The image is the permanent, unchangeable template created directly from your blueprint. It contains the application code, the runtime, and all the system tools. The keyword here is immutable. It's an immutable template, meaning if you want to change your app, you don't edit the image itself. You update the Docker file and you build a brand new image. And finally, we have the Docker container. If the image is the template, the container is the physical runnable manifestation of that template. It's a lightweight, standalone, and executable instance that holds your live application. You can spin up 1, 10, or 1,000 identical containers from just a single Docker image. Now, what's really interesting about this is how Docker manages all of this data so efficiently. Docker images are actually built using union file systems and image layers. Each instruction in a Docker file creates a new immutable layer, and Docker just stacks these layers on top of each other. So if you change one line of code at the very top, Docker doesn't rebuild the entire OS at the bottom. It just uses the cached, unchanged layers. This saves massive amounts of storage and makes build times incredibly fast. When a container runs, Docker simply slaps thin, container-specific writable layer right on top of those read-only image layers. Pretty clever, right? Section 4. Under the container hood, Linux magic. Okay, it's time to get a bit technical because I want to prove to you that containers aren't just magic. They are a brilliant application of built-in Linux operating system features. So when a developer types Docker run on their machine, an intricate relay race kicks off behind the scenes. Step 1. The Docker daemon receives the request. It checks if the image is available. In step 2, it passes the request to Containerd, which is the high-level manager that handles the container's lifecycle. Step 3, Containerd hands the actual execution off to a low-level runtime called run. And finally, in step 4, run communicates directly with the Linux kernel to create that isolated environment. And that isolation relies entirely on two highly specific Linux kernel features, namespaces and cgroups. It's absolutely crucial to understand the separation here. Namespaces isolate what the container can see. They give the container its own isolated process tree, network interfaces, and mounts. To the container, it feels like it's completely alone on a server. Cgroups, on the other hand, or control groups, limit what the container can use. They put strict constraints on CPU and memory, making sure that one greedy container can't just gobble up all the resources and crash the entire host system. Moving to Section 5, running multi-container apps beyond the single box. The reality is, modern software almost never lives in just one box. It's usually a complex web of interconnected services. And this is exactly where Docker Compose comes in. Instead of running a dozen different Docker run commands and manually trying to link networks together, Docker Compose acts as a declarative tool. Using just a single, easily shared YAML configuration file, you can instruct Docker to simultaneously spin up a web server, a database, and a caching layer, complete with all their specific volume and network configurations. It's a real game changer for workflow. Speaking of networks, these containers actually need to talk to each other safely. Docker provides a few different network drivers to handle this. The bridge driver is the default, offering a private internal network for your containers. Then there's the host driver, which removes network isolation entirely if you're looking for maximum performance. Overlay is used to connect multiple containers across entirely different physical machines, and none provides complete, air-gapped isolation for when you want a container totally cut off. Finally, Section 6, Scaling Up, Orchestration Showdown. Because think about it. What happens when you don't just need 3 containers on your laptop, but you need 3,000 containers deployed globally in production? And this brilliantly illustrates the landscape of container orchestration. Based on a 2018 study from the Journal of Applied Pharmaceutical Sciences and Research, we can see a benchmark comparison between the two heavyweights in the space, Kubernetes and Docker Swarm. Across metrics like auto-scaling, self-healing, ecosystem maturity, and resource overhead, the data shows two very, very different design philosophies. So what are the actual trade-offs? Well, Docker Swarm is lightweight, it's developer-friendly, and it's perfectly integrated right into the Docker ecosystem. You can activate it with a single command, making it absolutely ideal for quick setups and smaller teams. On the other side, you have Kubernetes. Originally developed by Google, it has a famously steep learning curve and higher resource overhead. However, it offers incredibly robust auto-scaling, dynamic scheduling, and self-healing capabilities. Literally, if a node fails, Kubernetes automatically reschedules it. Swarm is perfect for simplicity, but Kubernetes is the undisputed heavyweight champion for massive, complex, global-scale applications. We've covered a lot of ground today. We've gone from the ports of physical shipping all the way down to the Linux kernel, and then back up to global cloud orchestration. You now have a really solid structural understanding of how containers virtualize the OS, how images stack layers to save space, and how orchestration keeps the whole shebang running smoothly. So, I leave you with this. Now that you understand the mechanics, what complex workflow in your own life or organization will you containerize first?